Okay, we're continuing with Chapter 12 in the statistics textbook. In this video, we're going through the second section, which talks about the method of least squares. So it's a little bit confusing how exactly least squares relates to regression. And, is least squares a regression technique or isn't it? If you do some research on this, you'll find different sources seeming to say that least squares isn't regression, but then other sources saying that it is. Okay, and so I'm not a statistician. I'm a mechanical engineering PhD. I plan to become a professor. So I've got a lot of experience with math and statistics. Okay, but I had to do a little bit of research on this to get an official answer to what's going on here. Okay, and so I think you'll find this pretty interesting as we go through this section in this video. I'll give you a clear answer on what exactly is least squares. Is it regression or isn't it? And how is it related to the fundamental regression method that we learned a few chapters ago? Okay, so if we come back to Chapter 8, or no, it was Chapter 10, where we were officially introduced to regression. Okay, if we look here, we've got this summary sentence for what the regression method is. Okay, so it says, this way of using the correlation coefficient to estimate the average value of y for each value of x is called the regression method. So that's it. It's a curve-fitting method, which for any curve-fitting method, you're trying to estimate the average value of the output variable given the input variable. Okay, so the part of the sentence that says you're trying to estimate the average value of the output variable for each input variable, that's curve fitting, right? But what makes this the regression method is that we're using the correlation coefficient to do this. Okay, and the way we're using the correlation coefficient is we just say, so if we have an input variable, we can translate that to a z-score and say, okay, if we're given an x value, we can say, okay, how many standard deviations away from the average is that x value? Okay, and so now we're at that position away from the average with respect to the x variable, right? So then it's all about, so here's the scatter plot, here's the point of averages. Okay, so we're given some x value above or below the average, so we're here. And so the question is, how far up do we need to go to estimate the point of averages for this x value? Well, the amount that we go up or down is, so however many standard deviations this is, we translate that to the same number of standard deviations in the y direction with respect to the y variable, but we multiply, instead of going that number of standard deviations in the y direction, which would put us on the SD line, we multiply that by the correlation coefficient. So we only go up a fraction of a full standard deviation in the y. And that's it. That's the regression method, right? You can see how we make direct use of the correlation coefficient to do this. That's why it's called regression. And so you can have other curve-fitting methods that aren't called regression because they're not making direct use of the correlation coefficient. Okay, so now, what is least squares? And why is it sometimes called and sometimes not called regression? If we look at the title here, it says the method of least squares. It doesn't say regression, right? So let's take a look. Chapter 10 discussed regression from one point of view, and Section 1 went over the same ground using the regression equation. Yeah, so we just took if you start at the point of averages, then the slope of the regression line is this. So point slope, you have a regression equation. Okay, this section is a third pass at the same topic, yet from another perspective. The same topic of regression. Okay, for statisticians, regression is an important technique. So we're talking about regression. So, okay, if we're talking about least squares and we're talking about regression, I guess that means that least squares is regression, right? Maybe. Okay, so sometimes the points on a scatter diagram seem to be following a line, The problem discussed in this section is how to find the line which best fits the points. Usually this involves a compromise. Moving the line closer to some points will increase its distance from others. To resolve the conflict, 2 steps are necessary. First, define an average distance from the line to all the points. Second, move the line around until this average distance is as small as possible. To be more specific, suppose the line will be used to predict y from x, then the error made at each point is the vertical distance from the point to the line. In statistics, the usual way to define the average distance is by taking the root mean square of the errors. This measure of average distance is called the RMS error of the line. It was first proposed by Gauss. See the chapter opening quote, okay? The second problem, how to move the line around to minimize the RMS error, was also solved by Gauss. All right, so it says, among all lines, the one that makes the smallest RMS error in predicting y from x is the regression line. Okay. And well, yeah, and then it says, for this reason, the regression line is often called the least squares line. The errors are squared to compute the RMS error, and the regression line makes the RMS error as small as possible. The RMS error of the regression line was discussed in the previous chapter. Okay, so what are they saying here? Well, what they're saying is that if we've got a scatter plot of points that we want to perform linear regression with, okay, we want to do linear regression, get the regression equation, or just get some specific points, however we want to do it. Okay, we can obviously use the method that we've learned how to do in the previous few chapters that we learned in the previous section, right, with the equation of the regression line. Absolutely. Okay, but what they're talking about here is there's just another perspective of looking at how we can calculate the equation for this exact same line. We can look at the meaning of this line from the perspective of least squares, the method of least squares, to where all you're doing when it comes to least squares is you're starting with what you can think about as kind of like this flexible, undefined line that goes through the point of averages, that you can move it, right? And there's this, you have the vertical distances are parallel to the output axis of all the points to the line, right? And like the average magnitude of those points is we use the RMS. And with least squares, you're using, use like calculus, I believe, you get like an equation for the RMS error, and you do like differentiate and set the derivative equal to 0. And what you're doing is you're finding the line that minimizes the RMS error. And then you stop, boom, and that's the regression line. Now, it's kind of confusing because it makes it seem like, well, maybe least squares is a more accurate version of what the regression that we learned previously, right? We got a certain RMS error with the baseline regression method, but now least squares is even more accurate. We're getting an even smaller RMS error. Well, no, that's not the case. It just turns out that the fundamental regression method, outside of least squares, just with you have a point going through the point of averages and a slope given by this, that gives you that is the line with the smallest RMS error. There's no other line that you could make that's going to have a smaller RMS error. Okay, so what are we talking about here then? Well, what's least squares all about? And again, is least squares regression? Well, okay, what you can think about is that this method of least squares, okay, if you think about the idea of least squares from a big picture perspective, then no, it's not regression. It is what the title says here. It's the method of least squares. The method of least squares in general is an approach that you can apply to all kinds of circumstances outside of curve fitting, outside of regression. You're trying to find the optimum whatever it is, even if it's not curve fitting, the optimum whatever, by minimizing the error. Okay, now minimizing the error in what sense? Well, the way we quantify like the average magnitude of error is with the RMS, right? But again, this is not just with curve fitting. This is with any kind of process in science and engineering, right? You're trying to find the optimum, whatever it is, by minimizing the error. Okay, but what does that mean to minimize the error? Like you have to be more specific. Okay, well, you're minimizing the kind of the average magnitude of the error, and that's the RMS of all the error values. That's the method of least squares, which, again, it can apply to all kinds of circumstances, problems outside of just regression or curve fitting, right? However, for the case where you are using least squares to get like a regression line, then in those contexts, you might call it least squares regression, okay? And then, but furthermore, what you can see is that a lot of people, textbooks, etc., might like to just go ahead and say, well, okay, instead of looking at the regression method from the fundamental baseline perspective, let's just go ahead and look at it from the least squares perspective. That's more intuitive, right? From the perspective of least squares, you have a better sense of what's going on. Here, this is kind of ambiguous. I mean, yeah, we know we're using the correlation coefficient, but how exactly we're getting the best fit line is kind of hard to see. But when you look at it from least squares, the least squares perspective, now you really understand what you're doing, right? You're minimizing this RMS error. But then another thing you can think about is that you just want to get used to applying the least squares method, right? If you're going to do linear regression, we'll just get used to the mechanics of minimizing the RMS error of the curve fit. You get good with least squares, then you can apply that technique to other applications, like even maybe like non-linear curve fitting, right? If you have like an exponential curve fit, something like this. Well, maybe in that case, there's not just some simple correlation, non-linear correlation coefficient you can use with a simple formula like this, right? You can't. There's nothing you can apply as far as to obtain these points of averages for this exponential curve fit. There's no simple little formula you can apply like this. Well, when you think about it from the least squares perspective, you know exactly what you're trying to do. You're trying to minimize the RMS of all of these values. So you see, the least squares method is a more all-encompassing universal perspective that you can apply to a wide range of circumstances. Okay, and again, that's why a lot of you watching this playlist never really heard of regression from this fundamental perspective of the correlation coefficient times sigma y over sigma x is the slope, with the point of averages being the point that the line goes through. You've only really heard of the idea of least squares. That's why. Okay. So that's really interesting. I thought that was really interesting. Okay, now, an example, Robert Hooke was able to determine the relationship between the length of a spring and the load placed on it. He just hung weights to different sizes on the end of a spring and watched what happened. When he increased the load, the spring got longer. When he reduced the load, the spring got shorter, and the relationship was linear. Okay, let B be the length of the spring with no load. A weight of X kilograms is attached to the end of the spring. As illustrated in figure 4, the spring stretches to, so yeah, like this is Hooke's law. But when it comes to a spring, it's well known that the relationship between the deflection of the spring and the load is linear. And you can apply this idea to a lot of, when it comes to like metals, right? Before they yield, it's really a linear relationship between load and deflection of the metal. So you can model it like a spring. There's a lot of things in engineering where, at least for some range of inputs, the relationship between load and deflection, there's no actual literal spring like you'd buy at a hardware store, but you still think of it as a spring because there's that linear relationship, or at least close to linear relationship between load and deflection. And so you can think about, if you're trying to analyze if there is a linear relationship, you could use that linear correlation coefficient, right? In engineering, how do you quantify, how do you say officially, okay, is there a linear relationship or not? Can I approximate this as a linear relationship? Well, you might want to use the linear correlation coefficient to decide that. But how do you officially make that decision? We haven't really talked about that up to this point in the playlist yet. How do you look at, I mean, obviously if R is equal to 1, then you're good, right? But like if R is not equal to 1, which we're going to see is the case here, it's close to 1, how do you make decisions on whether or not you can look at something as linear? What's too low of a correlation coefficient? 0.9, 0.85, right? Okay, so according to Hooke's law, the amount of stretch is proportional to the weight. The new length of the spring is this linear equation here. In this equation, M and B are constants which depend on the spring. Their values are unknown and have to be estimated using experimental data. So yeah, if there's no deflection in the spring, you still have the unstretched spring length here given by B. And then the spring constant is M. It's how stiff the spring is. If you have a higher spring constant, then for a certain amount of load, like the spring constant tells you for it's a quantification of the stiffness of the spring. The higher the spring constant, then it's going to take more load to deflect the spring, where Y is deflection and X is load. All right, table 1 shows the results of an experiment on Hooke's law done in a physics class at the University of California, Berkeley. Different weights were hung on the end of a long piano wire. The first column shows the load. The second column shows the measured length. So yeah, I mean, I don't want to get into too much mechanical engineering here, but so here's the table. Okay, and it says the correlation coefficient for the data is 0.999, very close to 1 indeed. So the points form almost a straight line, just as Hooke's law predicts. The minor deviations from linearity are probably due to measurement error. Neither the weights nor the lengths have been measured with perfect accuracy. Nothing ever is. Yeah, so you've got these points here that they aren't all collinear, but they're close, right? So we're obviously talking about how do we get the best fit line here? Well, we could just use the regression method that we've learned in the past few chapters, or we could use least squares for that to get the exact same equation. Yeah, so just let me remind you of that again. It's not like you're getting a different regression line equation with least squares than you are with the traditional regression method. It's the same equation. Just you're looking at it from two different perspectives. Okay, so our goal is to estimate M and B in the equation of Hooke's law for the piano wire. Okay, so we're trying to estimate these coefficients here. Now, they're not going to do this isn't a full breakdown of how to do least squares. We're just kind of doing an overview of what least squares is. You're going to need calculus to really go through the whole least squares process. Okay, so this is really just more about getting a sense for what least squares is. So the graph of this equation is a perfect straight line. If the points in figure 5 happen to fall exactly on the same line, the slope of that line would estimate M and its intercept would estimate B. However, the points do not line up perfectly. Many different lines could be drawn across the scatter diagram, each having a slightly different slope and intercept. Which line should be used? Hooke's equation predicts length from weight. As discussed above, it is natural to choose M and B so as to minimize the RMS error. This is called the method of least squares. The line Y equals MX plus B, which does the job, is the regression line. In other words, M in Hooke's law should be estimated as the slope of the regression line and B as its intercept. These are called the least squares estimates because they minimize root mean square error. If you do the arithmetic, here it is. Right, and so again, this is the least squares. If you use least squares to get M and B, this is what you get. If you use the regression method that we've done in the previous few chapters to get M and B, this is what you get. Exact same values. Right? It is natural to choose M and B so as to minimize the RMS error. This is the method of least squares. The line which does the job is the regression line. Okay? The length of the spring under no load is estimated as 439.01 centimeters, and each kilogram of load causes the spring to stretch by about 0.05 centimeters. There's no need to hedge because the estimates are based on a controlled experiment. The investigator puts the weights on and the wire stretches. Take the weights off and the wire comes back to its original length. This can be repeated as often as you want. There's no question here about what is causing what. the language of association is not needed. Of course, even Hooke's law has its limits. Beyond some point, the spring will break. Extrapolating beyond the data is risky. So yeah, they're just making a statement about if you've got a controlled experiment, which this here would be really controlled, right? This spring in a lab, you're putting different weights on, getting the measured length. I mean, there's no confounding variables here, very, very little, right? So you can really look deeper into the meaning of the regression line in that case than you can for the case of an observational study. You can really use that regression line to make a prediction about if you brought in a new weight that you didn't use to calculate the regression line originally. You can use that regression line to make predictions, assuming you calculate the regression line with at least a decent amount of points, not just like 2 points, right? But you can't really do that with an observational study, at least with as much confidence. I'm sure a statistician would say that in some circumstances, if you've done your analysis right, then you can allow yourself to make some predictions, but that's more of a general statement. Okay, the method of least squares and the regression method involve the same mathematics, but the contexts may be different. In some fields, investigators talk about least squares when they are estimating parameters, unknown constants of nature like MNB and Hooke's law. In other fields, investigators talk about regression when they are studying the relationship between two variables, like income and education, using non-experimental data. Right, so here's more of some insight into the differences between regression and least squares. In the context of curve fitting, least squares and regression involve the same mathematics, but just it's different perspectives, different contexts. With least squares, it was more of like parameter fitting. With regression, it was more about the relationship between the two variables. Right? Regression, it was the correlation coefficient and the two standard deviations. Least squares was more of we had a line and we wanted to estimate the best fitting parameters for the coefficients of this involved in the equation of this line. Okay, a technical point, the least squares estimate for the length of the spring under no load was 439.01 centimeters. This is a tiny bit longer than the measured length at no load, 439 even. A statistician might trust the least squares estimate over the measurement. Why? Because the least squared estimate takes advantage of all 6 measurements, not just one. Some of the measurement error is likely to cancel out. Of course, the 6 measurements are tied together by a good theory, Hooke's law. Without the theory, the least squares estimate wouldn't be worth much. Yeah, so you can think about how in some circumstances you might, with a really controlled experiment, and then like what they're saying here, this is backed by Hooke's law, this linear theory of the relationship between load and deflection with respect to a spring, right? Well, then you're thinking about the fact that the points don't line up exactly on a line. That's probably caused by measurement error. You're really thinking that it truly is a linear relationship. And so since the regression line is it's this best fitting line that encompasses all of the data points, then you actually trust what the regression line is saying that the deflection of the spring is, not actually the measured point itself. In some cases, you could argue that, right? Because you have like measurement error. It's the measurement error that's probably causing the points to not line up perfectly on a line. Okay, now let's go through these exercises real quick. It says for the men aged 25 to 34 in the Haynes 2 sample, the regression equation for predicting height from education is shown here. Predict the height of a man with 12 years of education, with 16 years of education. So with both of these, does going to college increase a man's height? Explain. So, okay, what was on page 58? So there was just some study on page 58 that involved heights of men, their ages, their education, etc., and they did a regression analysis relating the education to height and got this regression equation here for the regression line. So if we want to predict the height given the years of education 12 and 16, we just plug it into the regression equation. So we do 0.25 times 12 plus 66 66.75. Okay, then we do the same thing with 16 plus 66.75. So 66.75 and 70.75. Okay, does going to college increase a man's height? Explain. Well, no. Obviously, no. We've talked about this, that association and causation are two different things. You can have an association, a legitimate association, with the corresponding causation being completely ridiculous. You can absolutely have that. You can find an association between anything, right? And so, but why is there an association here? Where is this association coming from? Because the older the man, their heights are going to change as they get, in this age range. Going from age 25 to 34, men might grow a little bit. And the older you are, then the more years of education you have. But it has nothing to do with your education. Because you're studying, you're growing. No, it's because you're older. The more years of education you have, the older you're going to be in general. Okay. For the data in Table 1 on page 209, the regression equation for predicting length from weight is shown here. Predict the length of the wire when the weight is 3 kilograms and 5 kilograms. Does putting more weight on the spring make it longer? Explain. Okay, so here's this Table 1. I don't think we're going to need it. And so there's the regression line equation for this data. And so if we plug in 3 kilograms, so 3 times 0.05 plus 439.01, the units match up, right? Centimeters per kilogram, and we're in kilograms. Okay, now let's do the same thing, but with 5. So we've got 439.16 and 439.26. And this is in centimeters. Okay, so does putting more weight on the spring make it longer? I mean, yeah, it does, unless you're calling into question the fact that this isn't a large enough change in length based on like the measurement uncertainty of the measuring device. But if you're assuming that these are legitimate measurements, then yes, I mean, we did. So what are they saying here? Okay, so maybe they're trying to illustrate how this 3 kilograms and 5 kilograms, they didn't technically use these values to get the regression equation, but that's fine. We're right in the middle of the regression line. We're not at the ends. So, I mean, we didn't even need to do this little experiment here with 3 kilograms and 5 kilograms to answer this question. We could have just looked at the data, assuming that for this particular experiment, you trust just having 1, 2, 3, 6 data points. Okay, but all we're doing here is just picking some other values that weren't originally used to make the regression equation, but that's fine. Let's see, we get 439.16 for 3 kilograms, and then we get 439.26 for 5 kilograms. That makes perfect sense with what the regression equation was made based on. So yeah, it does. The table here and the results we just got line up with the statement that putting more weight on the spring makes it longer. Okay, a study is made of math and verbal SAT scores for the entering class at a certain college. The summary statistics are shown here. The investigator uses the SD line to predict VSAT score from MSAT score. So, okay, so the SD line. So we've got these summary statistics, the average MSAT score and VSAT score, math and verbal SAT, for the incoming freshman at a certain college. There's the averages, there's the standard deviations, there's the correlation coefficient. Now the investigator uses the SD line to predict the VSAT score from the MSAT score. If a student scores 680 on the MSAT, the predicted VSAT score is what? So using the SD line, what that's saying is you're pretty much ignoring you're ignoring the correlation coefficient is what you're doing. So if a student scored 680 on the MSAT, so we're trying to predict the VSAT, then okay, how many standard deviations is this away from the average MSAT? So 560 divided by 120, that's one standard deviation away from above average. So if we're going to be on the SD line, then we go that same number of standard deviations in the Y direction. So we want to go one standard deviation above average in the VSAT direction. So 540 plus 110 is 650. That's the prediction. Okay, if a student scores 560 on the MSAT, the predicted VSAT score is what's going to be the average. This is on the average. So actually for the SD line or the regression line, this would be the same answer. So we'd say 540. Okay. Okay, the investigator's RMS error is greater than, equal to, or less than this. Okay, well, we know that this is the RMS error for the regression line itself, right? Because this is R is 0.66. This is the RMS error for the actual regression line. All right, now, what exactly the RMS error is relative to the SD line, I don't think we ever explicitly talked about that. That wouldn't be the standard deviation in the Y direction, because that's the RMS error relative to like a horizontal line going through the point of averages. We're talking about the SD line here. Okay, but we can still answer this question because we know that we just learned in this section that the regression line is the line that minimizes the RMS error. So, okay, now we have to think about, well, maybe the regression line and the SD line are the same line. Well, we know that's not the case because the correlation coefficient isn't 1 or -1. So the RMS error for the SD line is going to be greater than this. Has to be. Because it's not the regression line. And this is the RMS error of the regression line. Okay, repeat the previous exercise if the investigator always predicts a VSAT of 540. So yeah, in this case, we've got this is what we talked about, how if you're not given an input and you have to guess an output, well, then you just guess the average. That's the only thing you can do. It's the best you can do, right? And the RMS error in this case is the actual standard deviation in the Y direction. Because, right, it's the RMS of the deviation of all these points from the average. That's the standard deviation. And so in that case, we know that the answer is, as far as part C, we know that the answer is going to be greater than as well, because this is the standard deviation in the Y, and we know that the regression line isn't horizontal. I mean, we just know that this is going to be not equal to 1, so it's going to lower the 110, right? Okay, but the other questions are, if a student scores 680 on the MSAT, well, yeah, the prediction is just always 540. That's what they're saying. The answer to part A and B is 540. They told us that. They're always predicting 540 no matter what. Okay, exercise 3 describes one way to predict VSAT from MSAT. Exercise 4 describes a second way, and regression is a third way. Which way will have the smallest RMS error? Regression. That's what we just learned. The regression line is the line that has the smallest RMS error of any other line that you could use. And in the exercise 3 and 4 was looking at this from the perspective of making predictions with the SD line, and as well as with the horizontal line that goes through the point of averages. And neither of those cases was that the regression line. So regression.